Okay, so let's talk about dimensional homogeneity. Okay? Dimensional homogeneity basically means that if you have an equation, both sides of the equation have to have the same units. Okay, remember we were doing something, we were doing, I don't know what it was, I'm going to just make this up. It was meter per second squared. And I was going to try to transfer this, and instead of going from meters to feet, right? And I go 1 meter is about 3.3 feet. Okay. And these cancel out and become feet over certain. I did the wrong thing and I had 1 meter over feet here, and I went to 3.3. When in the end, I was trying to get feet per second squared. Now, if I do it this way, I do not get the feet per second squared, right? So in other words, on the equation on this side, my units would have been different than this one. Okay, because I would have meters squared over feet seconds, where what I'm trying to get is feet over second squared. So if I do this correctly, and I have the 1 meter is equal to 3.3 feet over like this, now the meters cancel out. I'm going to have feet over second squared on this side, and on this side, I'm going to have feet over second squared also. Dimensional homogeneity, okay? In other words, on both sides, I'll have the same unit, okay? So let's see if we can do that. Let's go to 6.6, example 6.6, and see if we can work this out. Example 6, when a constant load is applied to a bar with a constant cross section, as shown in figure 6.5, the amount by which the end of the bar will deflect can be determined from the relationship D is equal to PL over AE. Okay, in other words, we have a plate and we're actually yanking on the bottom. And when it says deflect, it means that it's going to expand or be lengthened a little bit. And that lengthened amount that it's going to be lengthened is D. Okay, that is D. That is this guy right here, which would be what unit do you expect this to be in? It would be in length, right? Some sort of length, correct? Okay. So if you look over here and there it says where D is the end deflection of the bar in meters, P is the applied load in newtons. So this guy would be in newtons. This guy's going to be in meters. L is usually length. It is the length of the bar in meters. Okay, A is going to be what? A is the cross-sectional area in meters squared. And E is going to be the modulus of elasticity. So what is the units for the modulus of elasticity? So what you're trying to find here in the end, what they want you to find is to find the units of this guy. Okay. In order to find the units of this guy, you have to solve this equation for E, right? If I do that, and I move this over, I can multiply both sides by AE, I get DAE is equal to PL, and I divide both sides by DA, and then I'm gonna have E left over. Okay, so I'm trying to find out what this unit is, right? What the unit of this guy is, right? So I have E is equal to PLDA. Okay, now let's just talk about the units now, okay? P was what? P was the applied load in newtons. So this is going to be in newtons. This is going to be in meters. L was the length of the bar itself, the original length. This would be the how much it expanded or deflected. So that would be in meters also. A is the area, cross-section area of the bar in meters squared, right? So this guy and this guy cancels out. I get Newton per meter squared. And is that the, yeah, Newton per meter squared, right? So that's what they're talking about. That's what we're trying to find. That was the answer. Okay, that was A. B. B is heat transfer rate through a solid material is governed by Fourier's law. Fourier's law looks like this. Q is equal to Ka delta T over L. Okay, and this is part of your homework, right? This is part of 6.2 homework, the Fourier's law, looking to see what it is. Okay. So this is a heat transfer across something that looks like this. Okay, so you're gonna have heat coming through here and coming out here. So A would be what? The cross-sectional area. K is just a constant. The delta T is the temperature difference between the inside and the outside. And L is the width of this. Okay. Okay, so that's that. So that's the Fourier heat transfer. And what are we trying to find? What is the appropriate unit for the heat transfer Q? So we want to find the unit for Q. So the unit for Q is going to be the same as the unit on this side. So let's see what we have over here. K is a constant and is within the thermal conductivity of a solid material in watts per meter degree Celsius. So it's going to be in watts per meter degrees Celsius. A is the area, so it's going to be meters squared, I'm assuming. Yeah, meters squared. Then I'm going to have delta T. Delta T is going to be in degrees Celsius. Then L is going to be the thickness of the material, which is M. Okay. So the degrees Celsius cancels out. I have 2 meters on the bottom, 2 on top. It's going to be in watts. So the Q, the heat transfer rate, is going to be in watts. Okay. So you see how we use this? So it's kind of loosely as equivalent. I mean, we're not dealing with the numbers here. We're just doing a unit analysis, wanting to make sure that this guy and this guy are both having the same units. Okay. And then there's numerical versus symbolic solutions. We're good with that. Let's go to example 6.7. Let's do example 6.7. Example 7, we have determine the load that can be noted by the general relationship among is explained in detail. At this time, don't worry about the understanding of these relationships. The purpose of this example is to demonstrate the difference between a numeric and symbolic solution. Okay, the concepts that are used to solve this problem are F is equal to M1G, F2 is equal to M1G, F2 is equal to A2 over A1, F1, we're blah, blah, blah. Okay, so numerical solution. So what are we trying to find? Determine the load that can be lifted. Okay, so by starting making the use of the given data and substituting them into appropriate equations, we can find the following. So I know that I have 100 kilograms there on one side, and the load on the other side I do not know. But I do know that F1 is equal to M1A, A being M1G, I'm sorry. So M1 is 100 kilograms times 9.8 meters per second squared. Where did that come from? This is the gravitational constant. 908-1 kilogram meters per second squared. okay, which is newtons really. So it'll be 981 newtons. And then, so F2 was equal to A2 over A1, F1, A2 over A1. A2 has a radius of 5, so pi r squared. A1, this is 15 actually. And then over here I have 5 squared A1, 981. So I'm going to get this is centimeter squared, is it? Centimeter squared. This was newtons. Pi's cancel out, centimeter squared cancel out. I'm going to end up with newtons here. So it's going to be 225 over 25, 981. So this would be 9 times 981 newtons. 9 times 981 is 8829. 8829 newtons. Okay? So that's how you can cancel that. Numerically, that's how you cancel it. I do it, right? Symbolically, okay, how would you do that? Symbolically, the way you would do it symbolically is that you would just say basically is that the radius of R2 versus the radius of R1 is a 3-to-1 ratio. 3-to-1 ratio, but because it is the area, which is dependent on the radius squared, you would have to square that ratio. So 3-to-1 becomes 9-to-1. And that's where this 9 here shows up. 9 times the 981. So that's a symbolic way or a more interpretive way to solve this equation. That's what they mean by numerical versus symbolic. Okay? So it's 9 times the 100 kilograms is what you can carry. So it's 9 times that, so it's 900 kilograms. Okay? All right, so that's that.